Hey everyone, it's time for the rubber to hit the road because it's going to be now that we start talking about routing. I want to introduce it and we're going to go into it very, very slowly, but what we need to understand is exactly what's going to be required of us by Cisco to demonstrate that we understand how routing operates. And there's no better way to do that than to explore the basic functions of routing as it exists in our infrastructure today. So first of all, we've already defined the role of a router. The router's job is to be able to connect different network segments together. That's basically its operational component, its role, where it fits into the grand scheme of things. But what we haven't talked about yet is this right here, what we're referring to as the routing table. The routing table, at its very minimum, is going to be a list of interfaces and IP addresses, or actually networks, that are going to be part or running on those interfaces. So what we see here is that in this scenario, each of these interfaces are connected. Fast Ethernet 00, Fast Ethernet 01. We can see 00, 01, and we can see the networks that are attached on either side of this router. So in other words, when information arrives from this or to this router destined to this particular network, what's going to happen is the router is going to look at the information. It's going to look at that packet, because that's what we're talking about right now, layer 3 packets. And it's going to look at its routing table and say, oh, it's destined to 192.168.1.0/24, that network. It's going to go down this list and it's going to find this interface. It's going to switch it from one interface to the other, and then it's going to serialize it out the circuit. Then everything that takes place is going to take place at layer 2, like we've already been discussing up to this point. So, but keep in mind that this routing table is exceedingly important. And the routing table is going to contain information associated with different types of routes. There are going to be connected routes. There can be static routes. There are going to be dynamically learned routes. And it's all going to boil down to exactly what protocols and how we have our systems configured that are going to determine the behavior of these routing devices. But at the end of the day, what we're going to find out is that routers are going to be best described based on specific characteristics. Now, the characteristics of a router are going to extend to its CPU, its memory, its ports, its configurations, its iOS. Everything that we see right here, CPU, motherboard, memory, different types of memory. We have random access memory, we have read-only memory, we have flash, compact flash, we have ports, we have network configurations, and we have management interfaces like the console ports that we talked about when it comes down to managing each and every one of these devices. Now keep in mind, it's also going to give us the capability of having WANs, and WANs with regard to media ports and access control to who has what privileges and what rights to do different things. Now, the crux of the matter boils down to one thing. Our routers have a routing table. I mean, that's the benefit of it. We're going to talk about how we have other abstract concepts like databases and things like that, but at the end of the day, the functionality of a router and its role is going to boil down to what's inside of its routing table. Let's take a look at this portion of the presentation and walk through what those options are. First of all, if I want to see the routing table, all I have to type is show IP route. And that's going to give me all of the routing information. It's going to give me information about connected interfaces. It's going to give me information about local interfaces. It's going to give me information about static prefixes that I may have configured in my system. It's also going to give me other values. For instance, notice here I have an O, where O actually corresponds to OSPF. B corresponds to BGP. And D unwittingly corresponds to EIGRP. These are all dynamic routing protocols: OSPF, BGP, and EIGRP. Now, in the confines of our studies, there's another one that we'll need to know called RIP version 2, and that's going to actually translate to everything that we're possibly going to need to know in order to work with and manipulate routing in the context of our devices. But at the end of the day, it all really boils together when we start looking at what happens. And routers do one thing. Routers are to allow us to send information from one network to another. However, what we have to understand is that routers make intelligent decisions about information that's provided about the routes. That means a router is going to either load balance across multiple links, a concept called equal cost multipathing or load sharing, or it's going to pick the best way to get to a destination. Let's explore that. So what we're going to find here is that when we have our devices configured, I could be running any type of routing protocol. Remember, we mentioned RIP version 2, we mentioned OSPF, we mentioned EIGRP, we mentioned BGP. Now, in this scenario, we're running OSPF on this path, and on this path, we're running EIGRP. Now, the decision as to which one of these routing protocols the system is going to make is going to be based on how we learned the prefix. So if I want to reach this location right here, notice I have all kinds of ways that I could go through this infrastructure to get there. Now, a routing protocol is going to want to select the best path. The best path is going to correspond to different parameters. We're going to have to understand a concept called administrative distance and a value called metric. Now, what this means is that between these two protocols, administrative distance is going to be most important because each one of these routing protocols have an administrative distance assigned to them, and it's going to attest directly to their believability. So if I learn a prefix, and it's an internal prefix from OSPF, it's going to have a believability, an administrative distance of a numeric value of 110. EIGRP, for an internal prefix, is going to have an administrative distance of 90. When it comes to AD, the lower, the better. So the lower administrative distance is going to be how the system is going to decide to send traffic. So in this scenario, it would actually send the information across the EIGRP link based solely on the administrative distance, which is a fixed value. We can manipulate it as administrators, but right now it's kind of outside the scope of our conversations. All we need to understand is routing protocols all have this idea of administrative distance, and let's explore those. When it comes to administrative distance, the AD for RIP is going to be 120. The administrative distance for internal prefixes for OSPF is going to be 110. EIGRP is going to be 90. And for internal prefixes, BGP is going to be 200. Now, what I want you to understand is that lower the better, but at 255, it's considered to be unbelieved. So it's unbelievable. So in other words, 255 is never going to be incorporated in the routing table. Now, the other thing here is that we also have another rule that's related to routing. The longest prefix trumps everything. So if I have two ways to get to a route, irregardless of what routing protocol advertised it, if one is longer than the other, it's going to be that one that I pick because it's going to follow the idea of best path or most specific routing. Now, outside of that, if we learn about prefixes from two different routing protocols and they're the same prefix, we're going to pick the one with the lowest administrative distance. If we learn something from the same routing protocol, administrative distance is off the table as a tie breaker, and it's going to fall down to metric. If the metric, i.e. the cost it takes to get information across each of those paths is the same, we're going to use equal cost multipathing. If it's different, we're going to pick the lower of the ones that we've learned. So keep in mind, this is going to be extremely important with regard to understanding exactly what's going to happen in our infrastructure. And it's going to be those prefixes that are deemed best that are going to be actually installed in the routing table. So of the ones that I have, it's going to be the best one based on administrative distance, based on metric, AD if it's more than one routing protocol, metric if it's within the same routing protocol, that are going to be incorporated into the routing table. Now what we have to understand here is another key element of information, and that is that in an IGP protocol, BGP is a border gateway protocol, it's an external gateway protocol, it's not going to fall into that category, but when it comes to RIP, EIGRP, OSPF, what we need to understand here is these routing protocols all recurse to a physical interface. So the system is going to have to know how to, or what interface to send the information out of. Now we're going to find that we have different flavors of routing protocols. We're going to have a distance vector variety, and we're going to have something referred to as a link state variety. Now, you're also going to have probably heard in your studies that EIGRP is classified as a hybrid routing protocol. That's bumpkus. Okay, EIGRP is just an advanced operations distance vector protocol, and we'll look at each of those in turn. But the main thing that we have to realize here is it's significant that our routers all identify serial interfaces or physical interfaces, serial or Ethernet interfaces to send information out of. Because what will end up happening is a packet may arrive on this router that's destined to this device. Now, the system is going to have to look at the routing table and find out the prefix. Let's say this network was this is 10.1.1.0. So when I look at 10.1.1.0, it's going to say it needs to go out this interface. This is that process of recursion that I'm describing. But what I need you to understand is that it's going to arrive as a packet and it's going to be routed. But before we can actually route it, we need to switch it, which means we're going to have to take it from this interface buffer and send it to this interface buffer so that it can go out on its merry way and reach its destination, 10.1.1.0. Now, the network, 10.1.1.0. So as we're looking at this, it's important. It's important for us to understand exactly what's happening and how this routing table has the capacity and the capability of influencing every routing decision that we have take place in our infrastructure. Now, again, I mentioned types of routes. We have connected routes. We have the idea of local routes. Local routes are just simply going to be /32 prefixes on our connected routes. We'll talk about why we do that later on in our studies. It'll be in the higher part of your CCNP, but it's got to do with the fact that a lot of our routing protocols support multi-topology infrastructures. So I can have OSPF environments or EIGRP environments where I can pick which way I want a particular value of traffic to go. So it just gives me granularity of control. It's not really going to impact us in the confines of our current studies, but keep in mind that it's going to be via the show IP route that we're going to have some types of routes that I want to point out. I'm not necessarily talking about local and connected, or even, and notice here, this is going to be O. That stands for ODR, on-demand routing. Let's see. No, that's OSPF. What am I thinking? ODR is it even, it's a little O, I think. It's not even showing up on this list. Static, local, OSPF. Yep, see, O here means OSPF. Sorry. I was thinking ODR. D means the IGRP. S means it's a static prefix that was learned. S with a star, an asterisk beside it, means something special. The asterisk means a candidate default route. Notice I mentioned the fact that we have to have a gateway of last resort or a default gateway in a lot of scenarios so that we can actually get out to the internet. Remember in that part of our conversation. Well, what will happen here is this star means it can be used as a candidate default, and if it's selected, it's actually going to be entered into the system that says, as a last resort is 10.1.1.1 to reach network 00000. Now here's what that actually means. If we go down through here and we look at all of these prefixes, everything that we have on this device, and we don't have a specific match. Let's say I wanted to get to 192.16.22.0/24. And I start parsing my table. I look here, nope, doesn't go. Nope, doesn't fit. Nope, doesn't fit. Nope, doesn't fit. Nope, nope, nope. Then what's going to happen is I'm going to be left with this prefix. This means that if I do not have a more specific route to reach this destination, send it out this interface or send it out this prefix. Notice it says via 10.1.1.1, which means it's going to actually go out gigabit 00. More often than not, that means it's going to go out that interface to reach the internet, and once it gets to the internet, it's going to be our service provider's problem. All we need to realize here is our routing tables are going to allow us to affect and manipulate how our internal traffic is going to flow in our infrastructure across our routers and through our switches. And if we want to communicate to the network, we either need to be an internet, we either need to be running a routing protocol with the service provider, which is very highly unlikely. More often than not, we're just going to have a default route pointing out that way and rely on the service provider to send information back to us. So when we go through and we do the setups with this, it's important to understand that everything is related. Everything is related with regard to how our protocols are taking place. and how they're operating, and no more so will we ever see this expressed in the confines of dynamic routing protocols. Dynamic routing protocols, RIP version 2, EIGRP, OSPF, even BGP as a exterior gateway protocol. What we need to understand here is they all have different rules and different engagements, different methods of looking at things. Cost in one may be a low cost in another. A high cost in another may be a very low cost in another protocol. Administrative distances are different, but there are other values that we want to make certain that we look at. And what we have to recognize here is that based on the protocol that we're using, we're going to choose different metrics used to determine best path. Best path calculations can be based on the overall bandwidth, the overall assigned delay, the cost, or even something as simple as hop count. So if I was using hop count in this scenario, I've got 1, 2, 3 hops versus 1, 2, 3 hops. So in this scenario, I'm sorry, it's going to be 1, 2 hops, and then 1, 2, 1, 2, 3 hops versus 2 hops. So in this scenario that I'm describing here, if I was running RIP, the green path would get picked because it's got the lower number of hops. What we have to understand here is no matter what the metric is, lower is always better. So 3 hops versus 4 hops, 3 hops is going to get picked. Or it could be a sum total of all of my bandwidths. In this scenario, if I ran something like EIGRP, and bandwidth was my only category that I was using to determine best path, what would end up happening is I would have 2 gigabits of throughput versus 100 gigabits of throughput. And in all honesty, what would happen is if I was running EIGRP, my flow would go this way because it has the least delay, if delay was important. And then we can also assign cost values to our different links based on different categories or criteria. But bearing in mind that usually the higher the bandwidth, the lower the cost, which means there's an inverse proportionate relationship between these particular parameters. Another element that I mentioned previously was the idea of distance vector versus link state. Really and truly, the primary difference between these two boiled down to the fact that a distance vector protocol is going to operate based on exactly what the name implies. It's going to take information. So if I have 2 devices that are interconnected and they're routers, what's going to end up happening is if I have multiple ways to get through it, I have a distance, which means hops. So 1 hop versus 2 hops in this scenario. 1 hop would get picked, and the vector is going to be out an interface. We have more sophisticated routing protocols than those. For instance, the idea of a link state protocol means that inside of certain regions of our network, referred to as areas, what happens is every router knows the same information. So we exchange database information, and then based on the algorithms that we run, we're going to pick information that's going to make it into the routing table. So a link state database has a link state protocol has a link state database. Distance vector protocols typically don't. EIGRP has a comparable component called a topology table, but when we start looking at it, we're going to understand again that it's just basically a straightforward distance vector protocol. Nothing really special about it whatsoever. So like I said, this is the most fundamental explanation of what is involved in routing. We talked about the 3 key elements. The longest prefix match. So if I have 192, let me bring up my whiteboard. So if I have the network 192.168.2.3 or 0/24, and I have 192.168.2.4/29, I'm just arbitrarily picking numbers. Both of these can exist in my table, and if I was trying to get information to go to one of these, the one that has the longest match would be the one that got picked. So in other words, it's going to go with the most specific prefix. The other element that we talked about was AD, administrative distance. Administrative distance is going to be the believability of the information that we learned from an IGP. So between OSPF EIGRP and BGP, we have to understand that we have different values. RIP is going to have a value of 120 for its AD, its administrative distance. OSPF for internal prefixes is going to be 110. For external prefixes, it's going to be 110. For the idea of EIGRP, it's going to be 90 and 170. And for BGP, it's going to be 20 and 200. So 20 for, I'm sorry, I got this backwards. It's going to be 20 or 200 for an internal prefix, but from an external prefix, it's going to be 20. So what we're going to find here is these different values all have meaning based on the fact that administrative distance is used to pick a protocol when we learn, or pick a prefix, when we learn it from multiple protocols. The last element here was the idea of metric, and metric comes into play when we learn about the same prefix from the same routing protocol. Bearing in mind, no matter what the situation, longest match is always going to trump the process. So with that being said, we've wrapped up the basic fundamentals of EIGRP, of our routing protocols, and we also talked about the difference between distance vector and link state, in that link state maintains a database and there's a lot more moving parts, and it's also going to be higher utilization requirements with regard to our CPU and processing threads. So with that being said, I'll see you guys in the next video.